Okay, welcome back. What I want to look at again, and we're going to continue with, is level 3 NVQ diploma. Okay, and again, here we are. I won't need to read this out to you because you should now be familiar with this by now. Okay, and again, you should still be familiar with this by now. Okay, we're looking at session 10, and we're going to continue with cable calculations 2. Okay, you've seen cable calculations in session 9. So refer to that session 9 if you have to try and catch up, okay? Let's pull back to make sure we have it all in. Excuse me. Okay. And here we have the outcomes, okay, learning outcomes for this session, okay? The student will be able to gain a further understanding of cable calculations. And here we have faults, okay? So what I want to show you first is some of the faults you can see which can occur. Cables here being burnt, okay? Plug tops being burnt to cinder, okay? Simply called by overcurrent. And here again you have a cable here which is looking like it's beginning to burn through, okay? Okay. Let's get this panned in place, okay? And full. Now when we calculate the cable size, we are concerned with the ability of a cable to handle the heat generated in it by the flow of current and to take account of the many factors that will slow down the cable's ability to get rid of that heat before the insulation is damaged. Now, these factors include the surrounding ambient temperature, grouping, and thermal insulation. These we have already made use of. What about when a fault happens, either as a short circuit or as an earth fault? Let me explain that. You can read this for yourself in full, okay, as well. I don't want you to be in the dark about this at all. Okay. We're just going to pan back a bit, okay, so we can get it all in, okay. Okay, thank you. Good. Now make sure you read the information and you make your own notes. That is the intention of this, to help you to make your own notes and to be familiar with what occurs. And again, here we are continuing with fault current, okay? And I'm just going to bring this into place so you can see for yourself before I read it with an explanation given, okay? Okay, and I'm just going to pan back so we get it all in view. Okay. Now, fault current. In a fault, there will be a significant increase in fault current. This is caused by the load effectively being removed and replaced with a direct connection between line to neutral or line to earth. This increase in current has two direct effects: a rapid increase in temperature, a rapid operation of the protective device. Both of these will occur at the same time. Now, short circuit or fault to earth. Okay, and again, if you will have seen this in session 9. Okay, I'm just recapping this now basically so you are familiar with the effects. Just make sure that we have it all in. Okay. Okay, let's pan out a bit. Make sure that we can fit it into our screen. Okay. And I'll just drop that down. And we're looking at short circuit of fault to earth. Okay. Now again, a short circuit of earth fault occurs in the circuit, and we're looking at this in either way in regards to your protective device. Now you'll have seen this in session 9, so please feel free to look back. The fault current is very large due to a very small level of resistance. Ohm's law equals I equals V over R. Please note I is still old-fashioned, so I will still look at this as V over R or U over R. Okay. The fault current causes the fuse to blow or the circuit breaker to trip within a certain time, while the protective device is getting ready to operate, never instantaneous. While the protective device is getting ready to operate, never instantaneous, the cable starts to heat up. So what we're looking at here is that our fuse, let's assume that this is a rewirable fuse, the fuse will begin to heat up. So it's not going to instantaneously melt. It will have to acquire some heat first, and then current will continue to flow for a while. The concern here is that the length of time it takes for this fuse to melt is the effect it may have on that cable to your load, and it is the time it takes this fuse to blow that will determine the effect or the melting effect of the current going through the cable, thereby bringing about a large power surge. And that is what we need to ensure that we minimize, that the cable can handle the current up to the time that the fuse will blow or the circuit breaker will trip. Okay, and here we have timing. Okay, not timming, timing. Okay, I'm just bring this into play for you so you can see it. Okay, Now, timing. If the temperature in the cable gets too hot before the protected device operates, then it will permanently damage the cable, requiring replacement. The two separate aspects of this are called shock protection and thermal withstand. And here we're going into shock protection. Okay. Okay. We are seeking to ensure that the protected device operated within a certain time frame, and that whilst the fault existed, the protective conductor within the cable doesn't overheat. The operation of the protected device is shock protection, whilst the limiting of the heating effect is thermal withstand. And that is what thermal withstand is, that the cable can withstand the thermal effect of a limited time that the current will flow within the circuit. Now here we have thermal withstand, okay, and here we have the relevant regulations that stipulate it and will refer to it. Now make sure that it is concurrent with the 18th edition or any future edition that might come out in respect of the IEE regulations. Let me just make sure that we have this in view, okay. The thermal withstand. All fault current protected devices must meet the requirements for regulations 43.5. Now, take into account any changes that may have occurred in regards to this. So you'll be looking for your heading thermal withstand in regards to the IE regs. Okay. This means that the rated short circuit breaking capacity of each device is not less than the maximum prospective fault current at the point the device is installed. A fault occurring at any point in the circuit shall be interrupted within a time such that the fault current does not cause the permitted limiting temperature of the conductor or cable to be exceeded. And here you have the regulations which you need to refer to confirm and ensure that you are compliant with the regulations as it is of that point in time. When we deal with this current carrying conductors, we must ensure that the cable does not overheat. In regulation 434.5.2 of BS 7671, there is a formula T equals K squared S squared over I squared. Okay, and that's the formula you'll need to consider for thermal withstand. This formula tells us the time it will take a conductor to reach its final limiting temperature. Okay. Okay, now I hope you found this useful. That will be it for now, okay? Let me just pan back so we can make sure we get everything in place, okay? And thank you.